Okay, in the second part of this lecture, we will actually implement these four approaches to solve this least square and the and to solve this and the linear system with these four choices. And you can see right here we have this naive solver, we have a QR solver. So this is, I mean precisely as I mentioned right here, and also for the pseudo inverse approach and the least square approach, this is just one line of the coding. I'm running one demo. So this is some random examples that I propose. So this is a very ill-posed questions. And you can see, we create a random matrix for n by n. On the last column of this matrix will be basically the summation of the first n minus one columns. So if I don't do any perturbation, so this A will becomes a singular matrix and each column is linearly and dependable. However, I'm going to add a tiny noise for this matrix. So this will be very close to linear dependent, but turns out still linearly independent. B is also a random matrix right here. So we're going to try these four approaches. As I mentioned, these are all like the first one and second one are separate functions. The fourth and the first one and the fourth one are separate functions. The first one and the second one is just one line of the code. So you can see right here, this is the result for m equal to, I think this is pretty large, 500,000. N is 20. So you can see, actually, this is the performance right here. So in terms of the speed, we can tell. In terms of accuracy, this naive approach. So the residue you got is and 6 and 55, 4.75. So this is the residue right here. However, for pseudo inverse, this is 4 and 50, like 654.54. Same for and the same for the least square approach and the QR approaches. So all these three approaches has the same residue error and the same norm. And obviously this has a smaller residues compared to the naive approach. So, and basically this naive approach is not good at all. And in fact, it performs really bad. In the computer, you can see the solution is completely different. Just because the ill-postedness that we are working with. So that's why we are, in terms of accuracy, these three approaches are the same, and it's better than the naive approach. But in terms of time, so what you can do here is you can, using the percentage time, that just tells you I'm going to run this portion of the code. Then it will calculate how and the time that actually needed right here. So we can see if we are talking about these three part we have, so and the CPU time, this is giving you the time, like total is 6 right here, and this is 10, this is 4. So just, and that indicate the QR is farthest and fast one, and then that will be the pseudo inverse. The last one that, it's least square solvers. Okay, so, and you can see right here, so in terms of time, QR is the fast one. So like this is particularly true if you're working with a tall matrix. That means N is bigger than D. Then the QR method is the best. It's quicker and more accurate. If we are working with a back matrix, which is a complete different set of and a situation that we have more features than the number of points. then the other two approaches, pseudo inverse or least square solver, will be better than the QR. So this is actually just, and it depends on the problems and the setups. And sometimes if our D is so big, and that happens, and we will talk about this, then we will like use completely different approaches here. So let's try some synthetic and the data. We're going to create 51 and the data points. So then we're going to reshape into ones, but I want to emphasize we're going to add a column ones on the first, so like to ensure we include everything for the and for the intercept. So this is the true W that we are getting. And this is my Y, and of course we are going to adding some like Gaussian noises. And so the data that we have is just X and Y right here, right? So this is, and so like in general, we don't know this like ground truth of my W. We don't know the standard deviations of my Gaussian noises. So if we actually plot this out, it will, look something like this, right? So this is quite quite noisy here. So you can see, so the true like function one that we should be getting is a quadratic function. We have we have linear in terms of x and so quadratic in terms of x squared, and there's no intercept terms. So this is basically and like quadratic functions. But say we try, and this is the ground truth of W for that. So basically the ground truth of and the true W is, if we think about everything, that should be 0, minus 1.5, and 1 over 9. Right. So this is actually the true W here. I simply ignore the first and intercept right here. Okay, so but like say we are not using this quadratic terms, right? So for now we just assume we just try to do this kind of least and a square and regressions. So what we do is we just take this like least square and approaches. That means we just consider the and y is equal to W0 plus W1 times X. So this is a linear system, just a linear system. So we're using this QR solvers, and we can find out this W0 and W1. And in fact, we can do this like match and whole mesh grid right here. So you can see this whole loss function. So this is the function of RSS. So you can see this actually is look like an strongly convex functions. So this actually give you contours right here. So and you can see the contour plot right here, and you can tell this is center of this will be will be my local minimum here. So you can see this like, and the loss functions will be like and curved up. So this give you the surface look like. Okay, so we can plot out the true W, which is look like this. Obviously, this is completely different from the ground truth of W, because for the ground truth of W, we have the quadratic terms. And also we can plot this counter plot for this and RSS versus my W0 and W1. So this is the counter plot for the residue sum of squares. I'm in 2D. So you can see, so this is my ground truth right here. So this is actually the center. So that indicate, and this is the and the global minimum right here. And the way one that we actually calculate is truly and the minimum in terms of contour plot. So, and you can see this like level curve of RSS is all like ellipsoid. So, and that's expected because an RSS is basically quadratic functions and a sum of the quadratic functions. All right. So we can also, I'm actually plot out the predictor value. So this is actually the predictor values with the W0 and W1 times X. So this is our model here. So you can see this actually give you the fit. The fit is not ideal. You can see this is an obvious quadratic functions. We actually fit with a straight line. You can see there's a lot of deviation here, and it's not really good. So that's why, and the least square and approximation, it's very rough. So that, I mean, that indicate maybe you shouldn't just stick with the linear models. We need to add in more more polynomials and to that. So that's why in the next lecture we're going to talk about this nonlinear relationship, and this will make things much more complicated, and particularly, and I mean that case is then the dimension of the X data will be significantly larger. All right, so that's all for the and lecture 3 and implementation part. So this, I mean, just give you a quick summary of what kind of least square solver that I should be using to be the most stable and robust and efficient. So that will be just QR solver if this matrix is tall and skinny. All right, so that's all.